All right. So I'm going to talk a little bit about something a little bit different, but probably related to what most of you do, which is really looking at networks in maybe a slightly different way than what you have in the past. Most of this content won't be very new for most of you, so I'm going to go through it very quickly. But hopefully the model presented, although made up of common parts that you already understand, is something that's maybe useful to you. So really the idea here is redefining the ideas of core and access into a new two-tier network model. As you may have heard mentioned, I'm going to go through 63 slides in about 10 minutes. We'll see how well I do. But so obviously I need everyone engaged to do this. So just to start out with, quick show of hands, who can raise their arm? Little lag, but we're okay. All right, I think we're going to make it. Good deal. So first of all, what do I mean by a network model, right? So I think if we break that apart, most of us should know what a network is, right? We're trying to pass packets, we're trying to forward frames, we're talking about routers and switches, various middle boxing, and connections to pull them all together. So we get what a network is. But what's a model, right? Obviously, we're not talking about HO scale trains. We don't really want to 3D print a physical representation of the network. It may be fun, but not very useful. So what I'm really talking about here is a conceptual model. Right? If we look at Wikipedia, it says a conceptual model is a set of concepts, not super useful. An abstraction of real things, more useful. A representation of a system, I think now we're getting somewhere. Really it's used to help people know, understand, and simulate a subject. And that's what I'm really trying to talk about here. So obviously, a model is not the exact thing, but it's something we can use to think about that thing or talk about that thing that'll help us to build that thing. So I think that we have to start with the old model, which is the classic three-tier hierarchical model. So for a campus network, it looks like this: core, aggregation, access. For a data center network, it looks strikingly similar, but we've changed the name. It's now distribution, which I think is odd, and I think it's worth pointing out. At least, I don't know, I wasn't there when they created these names, but I think the reason there's two different names is because of this old client-server model, where what you're doing is aggregating client connections in a campus and then distributing them out to servers in a data center. Obviously, there's a return path there, but I think that's kind of why it's distribution versus access, which kind of brings up the other three in this model, which is LAN, WAN, and data center. And of course, really, we're talking about north-south data flows there, but I think I'm getting a little bit ahead of myself. So those three tiers, what we're really talking about is a core layer that's doing fast forwarding, right? You're really trying to pass packets. It's just big iron moving frames as fast as possible. The aggregation and distribution layers, both, are doing all of the routing, the policy, the ACLs, the load balancing. That's where all your services live. And so they have to be smart switches or routers. And then the access is really just for that, to access, to connect everything together, pulling it all together. And so I can't talk about the kind of three-tier network model as a legacy model without obviously mentioning leaf-spine and clause networks. So what happened, I think, is network virtualization came along, and we started having east-west traffic patterns. We started turning up and turning down services very quickly. We've got mobile workloads that move around, and we've got massive scale. Now, not all of those things are directly related, but they all kind of happened at the same time, which made us want to change the network. So we went back to 1952 to a guy named Charles Claus, who had created this framework, and actually it's a mathematical algorithm for using crossbar switches that you can connect together, and you can get non-blocking switch fabric that's way bigger than any switch can be economically built. The reason it was in 1952 is because we were doing some weird things with these crossbar switches. At the time, they were limited in what you could build for a certain price, so connecting them together in this way in a non-blocking fabric helped the telephone system happen. We then moved on to more advanced switches, and so we kind of fell out of favor, but now we're going back to this, really because that same thing, you can do this non-blocking fabric with multiple switches pulled together. This is a three-tier clause network. What we're doing is folding them in data centers today, and so you end up with this leaf-spine network. But spoiler alert, that's not the two tiers that we're talking about here today. So to jump back to the three-tier network model, there's some problems with it, right? I mean, that's why we're looking at a new model. So the first class of problems I would categorize as directionality. So we go back to that idea of client-server versus, service orchestration between modules of an application within a data center. So you've got this north-south versus east-west change. And then also just scale up versus scale out. So scaling up a network that's heavy with these three tiers, you have to move every single piece has to get bigger and bigger over time versus being able to add pieces to scale it out, right? So those are the two different directions you can grow. Also resiliency, spanning tree sucks. You get half the bandwidth. Also, again, back to that kind of scale up versus scale out. In order to get redundancy out of the three tiers, you have to grow all three tiers with big expensive boxes, right? You're talking about chassis, big iron at the core level, big chassis iron at the aggregation and distribution level, and just more and more boxes and hardware. which really one of the biggest problems here is that hardware centricity. The hardware layer is actually providing services, right? All those ACLs, all that stuff I was talking about in the aggregation and distribution layer, that's built into the hardware of that system, or at least the software that's tied to the hardware in kind of a mainframe style system. And so it's dependent on availability of that box, which means your physical connectivity is dependent on that, right? So you have to physically place firewalls, routers, load balancers in certain places in your network. You have to connect them in literally physical locations in order to get them to work, which can be a problem if you're trying to scale out or grow fast or do different things with the network. And then also it's slow, right? Typically it's a manual configuration, and then the feature velocity sucks because the software and hardware are tied together in that middle layer, and that's tied to actually swapping out boxes in order to improve the services you're offering, and all those things. Again, I'm going over a lot of this really, really quickly, assuming that most of you kind of get what some of these problems are. Happy to talk about it in more detail afterwards. So if server virtualization is what kind of caused this move towards new types of networks, the other part of virtualization that's really interesting that's happened more recently is network virtualization. And this is really two pieces, right? So network function virtualization, or virtual network functions, is taking the physical boxes and turning them into software, right? So you can have virtual switches, routers, firewalls, load balancers, ADCs, whatever, pretty much anything you can do in hardware, you can also do in software. Especially now with some advances in the way we're using CPUs and GPUs to do packet processing, we have some really cool things we can do. So that's network function virtualization. Then we can also virtualize networks. And this is kind of a typical drawing of how we draw virtualized networks. Obviously super simple, but we can actually make it a little bit simpler. So if we look at the smiley faces as users and the check marks as applications, then there's a bunch of switch routers in between that connect everything together. And when you're virtualizing a network, you're basically saying, I don't want the physical connectivity to matter. I really want the network to look like this. Usually that's done with overlays, which are sometimes a little bit scary or poo-pooed. But the thing about overlays is they're not new. We've got VLANs, we've got MPLS, we've got GRE, there's IPsec, there's SSL. You're probably using an overlay every time you use a computer or a network. And then also, actually beyond that, the optical ring of fiber in your city, and then the Ethernet connectivity between your buildings, and then the IP connectivity between your actual services is definitely a series of overlays, right? So we've been doing this all along, and so maybe an additional overlay isn't really that scary or that disastrous. So all of that kind of can come together into what I'm calling this new model. And all those things come together in a couple interesting ways, I think. One, I would call switch inception, right? So switches inside of switches. This folded clause versus a multi-switch chip is really what I'm talking about here. And by exploding this, maybe we can have a little bit more visibility and control. So let's look at that clause network again. You got the spine and the leaves. And then let's look at a chassis-based switch. There's a fabric chip and there's NPUs, and they're all kind of connected together. So just to make sure we didn't miss it, clause, multi-switch chip, as we can see, it's kind of the same thing. So what we've really done is kind of exploded that out, which is interesting. The next thing is the opposite, which I would call router explosion. So if you look at a automation framework or an SDN controller as a virtual routing engine, and then these virtual network functions you can place almost anywhere as virtual line cards. Then you can also use tunnels as virtual circuits, right? So again, if we look at a router, there's routing protocols that go into a routing engine that has a routing table, and it can push routing protocols out. That's connected, it's pushing the fib down to a line card, which is then connected to physical interfaces on both sides, right? And if we look at a SDN architecture, strikingly very similar. You can have protocols and APIs feeding into a controller, which has a routing table, which can then push fib entries down to virtual network functions, also can push policy and all kinds of other things. It can have physical or virtual interfaces on either sides. So again, kind of looking at that one more time, it's actually very, very similar. So you may see where I'm going with this now. You can have lots of routers in the middle here, or you can have a single distributed router. So if you push those VNFs, now the little X's that were switches and routers in the middle are in each end device there, so they're living either on the servers or in maybe your cell phone or your laptop at the end device. You have a distributed cluster of controllers in the middle there. Obviously, you still need physical connectivity, and that's where we get the two layers, right? So you have this idea of an underlay as a core switch. So your physical infrastructure is actually supporting packet processing, fast forwarding, and then you've got a software overlay, which is acting as your access router. There's some characteristics here. You need a non-blocking ECMP, you need resilient high bandwidth and physical devices in the underlay, right? And then the overlay is all about tunnels. You can do hashing over that ECMP. You can do policy-based routing, software-based routing, because you've got now unlimited CPU, essentially, for all of your routing devices, and then these virtual devices that tie it together, right? So routing, policy, services, and security are all in software, and then the connectivity obviously needs to stay in hardware. But we do have wireless networking. We don't have device-free networking, and probably won't for any time soon. So why does this matter? Why am I even talking about this, right? So I think theoretically, like using this conceptual model, you can really look at what matters, right? So you've got this kind of separation of church and state where you can say, okay, if I need more physical connectivity, I can add that, and that's completely separate from the services I'm offering on the network. And so you can look at where those functions actually need to live in software versus hardware, and where you need to offer certain things, right? And also, I think I get to it in a little bit. So in practice, right, you've got this scale idea, right? So TCAM's not really an issue anymore if all your routes are living in servers. And that goes into like tables, policies, right? I mean, the routing table it's gonna be really easy to store that if you've got kind of an, unlimited cloud scale routers. And then also the updates part, right? If you want to add features, so networks have traditionally been really hard to change because they're the fundamental underlay of everything we do. So you can break applications really easily, or whole corporations really easily by losing network connectivity. But if you detach the services that the network uses from the physical underlay, you can have a rock solid 5, 6, 7 nines physical underlay and still be able to change services rapidly and adapt to whatever your business needs as far as offering services or providing services to customers, because now you can have like a CI/CD pipeline on these services that only affect the people who are using those services versus the entire network connectivity, right? So you essentially create this universal network platform that provides consistency, simplicity, visibility. Potentially you can have this convergence of LAN, WAN, and data center networking where you're looking at the whole thing as one network. You can push policy and routes out consistently. You can have simplicity of use with this thing, and you have visibility into the entire thing, and obviously unifying those domains. Those use cases, I think, in service provider, which some of this is already being done in a lot of areas, and also in enterprise, especially if you look at like the move towards multi-cloud, right, where you have workloads living in different hyperscaler environments as well as multiple data centers. The ability to actually have a single network platform, I think, is fairly obvious. Some people don't want to use a controller. Okay, you can use EVPN, that's fine. What happened to OpenFlow, right? Anytime anyone brings up SDN, someone has to mention OpenFlow. Well, there's this thing out there called the internet, and it actually is an ECMP network that you can use as an underlay really well, and we're starting to, right? That's where the whole SD-WAN idea was, really using the internet as an underlay, building a service infrastructure over the top of it. And so you can do this without changing the underlay if you don't use OpenFlow. If you have to use OpenFlow for everything, then you need to change every device on the network. So that's why overlays, I think, work better than OpenFlow. And there's another interesting thing, which is potentially the return to end-to-end. We placed bets on IPv6 as kind of getting rid of these middle boxes, but if you move everything to software, you can actually have physical connectivity end-to-end, and the services can do what they need to do, where they need to do it, kind of. So to wrap this up, I did double the time. Actually, we're already at 13 minutes, so that was terribly slow. But the map is not the terrain, right? This is a model, not necessarily a reality. It's a tool, right? So the idea of thinking about your network in this way, in these two tiers, is really again, a conceptual model that you can use to think about where services should live, how you should upgrade things, how you should build things. And in summary, overlays are normal, models are helpful, it's a digital world, software is king, and use it too. An underlay to move bits, and an access overlay to provide services. Because if you want to find new solutions, you need to find new ways to see your problems. I did. Speed that up some more. Yeah. We did 13 minutes, not too bad. Any questions?
Hello. I mean, this was a really good topic and a good time to speak about it. We're seeing just in the industry as a whole, people really moving away from having multiple devices on-prem and going to, a dumb x86 box on-prem with all of their services now on one box. The ability to choose your virtual firewall, your router, your SD-WAN, and put that all on one appliance out on the prem. We've seen it simplify network management. We've seen it reduce costs significantly from a network perspective, where you were spending tens or hundreds of thousands of dollars on an MPLS network, and now that's going away and being replaced by SD-WAN with similar functionality and easier maintenance for customers to deploy. So I think this was a great time to have this talk, and this is really where the industry as a whole is going from a consumer base. It's simplifying the network, simplifying the architecture, and simplifying the number of devices that you have at an actual office. So, good stuff.
Thanks. Anyone else? All right. Thank you.
It wasn't really a question, it was sort of,
We'll also accept statements because,
yes.
yeah.
All right, who's up